A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
Imagine for a second that your computer doesn't just need a power outlet and a cooling fan, but it actually needs to breathe. I'm not talking about a metaphorical breath or some kind of advanced air intake system for a high-end graphics card. I mean, it literally needs oxygen and carbon dioxide regulated to a precise degree, or the processor quite simply dies.
It is a wild thought, isn't it? We have spent decades trying to make silicon more like a brain, and now, in early 2026, we are seeing the script flip entirely. We're starting to use actual brain tissue as the hardware itself. I'm Herman Poppleberry, and you're listening to My Weird Prompts.
And I'm Korn. We're back in our living room here in Jerusalem, and we've got a fascinating, if slightly skin-crawling topic today. Our housemate Daniel sent us a prompt that really stopped me in my tracks this morning. He wanted us to look into the world of biological computing, specifically what's happening over at Cortical Labs.
Daniel always has a knack for finding the stuff that feels like it's pulled straight out of a mid-century science fiction novel, but this is very real and very current. We're talking about lab-grown human neurons being integrated into silicon chips to create what they call wetware. It is a massive shift from everything we usually discuss on this show regarding artificial intelligence and large language models. We aren't talking about code anymore, Korn. We're talking about biology.
Usually, we're talking about weights, parameters, and massive server farms in the desert. But today, the frontier of computing is moving from the server rack into the petri dish. There was a report recently in New Scientist that really highlights how fast this is moving. Apparently, a cluster of human brain cells on a chip learned to play the video game Doom in just a single week. Not Pong, which was the benchmark a few years ago, but a full three-dimensional environment.
It sounds almost like a prank or a headline from a tabloid, but the underlying science is rigorous and, frankly, a little bit unsettling. When we think about artificial intelligence, we're thinking about simulated neurons. But here, the neurons are biological. They are alive. They are growing and forming physical connections, and that changes the entire paradigm of what we call a computer. We are moving from the era of digital simulation into the era of biological synthesis.
So, before we get into the heavy philosophical and dystopian stuff, let's actually define what we're looking at here. When we say biological computing or wetware, what is the actual physical setup? Because I think people hear brain cells on a chip and they picture a whole brain in a jar, which isn't quite right. It's more subtle than that, isn't it?
Right, it is much more granular. Cortical Labs uses something called the dish brain system. They take about 800,000 human neurons, which are derived from induced pluripotent stem cells, and they grow them directly onto a high-density microelectrode array. Think of this array as a grid of thousands of tiny sensors and stimulators. The neurons sit on top of this grid, and, as they grow, they naturally start to form synapses and networks, effectively wiring themselves into the hardware.
And the grid is the bridge between the biological world and the digital world.
Precisely. The electrodes can record the electrical spikes from the neurons, which is the output, and they can also deliver electrical stimulation to the neurons, which is the input. So you've created a two-way communication loop. The digital computer can tell the neurons something by zapping them in a specific pattern, and the neurons can influence the digital world by firing their own electrical signals in response. It's a literal interface between flesh and silicon.
It is amazing that 800,000 neurons can do anything meaningful. For context, a human brain has about 86 billion neurons, so we're talking about a tiny, tiny fraction of a brain's capacity. And yet, this New Scientist article says they learn to navigate a virtual environment in Doom. How does that learning actually happen? It's not like the neurons have eyes or hands to hold a controller.
This is where it gets really interesting from a technical perspective. In traditional artificial intelligence, we use backpropagation. You show a model a million pictures of a cat, tell it when it's wrong, and it adjusts its internal weights mathematically. But biological neurons don't have a backpropagation algorithm hard-coded into them by a developer. Instead, they operate on something called the free energy principle, a theory popularized by Carl Friston.
I've heard you mention that before in our late night kitchen debates. Is that the idea that biological systems naturally try to minimize surprise or uncertainty in their environment?
Biological systems want a predictable world because predictability is the key to survival. If the world is predictable, you can manage your energy resources better. So, the researchers at Cortical Labs set up a feedback loop. When the neurons made a move in the game that was successful, they received a predictable, organized electrical signal. When they made a mistake or hit a wall, they received a chaotic, unpredictable signal, basically white noise.
So the neurons are essentially trying to make the noise stop? They're seeking silence or order?
Yes, they physically reorganize themselves, growing new connections and strengthening others, specifically to make their environment more predictable. They are literally wired to seek order. By doing that, they accidentally learn how to play the game. They aren't trying to win a game of Doom because they enjoy the combat or the graphics. They are trying to minimize the chaotic electrical feedback they're getting from the chip. It's an existential drive for stability.
That's a fundamental difference in how learning happens. In silicon AI, the learning is a mathematical optimization. In biological computing, the learning is a physical adaptation. The hardware itself is changing shape to solve the problem. It's not just software updates, it's physical growth.
And that brings us to the physical infrastructure Daniel mentioned in the prompt. This isn't just a chip you can plug into a motherboard and forget about. Because these are living human cells, the hardware requires a life support system. We're talking about a setup that has to regulate carbon dioxide levels, oxygen flow, and nutrient delivery constantly. It's called a perfusion system. If the power goes out and the incubator stops working, your processor literally dies. It doesn't just turn off, it decomposes.
It gives a whole new meaning to the term system crash. You aren't just rebooting the software, you're losing the physical connections that represent the learned data. If those cells die, that specific intelligence is gone forever. You can't just copy and paste the brain tissue to another chip. You'd have to start from scratch with a new batch of cells and retrain them for a week.
That is one of the biggest bottlenecks and one of the most fascinating aspects. Silicon is incredibly scalable because you can replicate code perfectly across 1 million servers. But biological intelligence is unique and fragile. It's tied to the specific physical arrangement of those 800,000 cells. It's non-fungible hardware. Each chip has its own personality, its own quirks, and its own specific way of seeing the world.
I want to dig into that fragility for a second. Why would we ever want this? If silicon is faster, more durable, and easier to replicate, why are companies like Cortical Labs pouring millions into keeping petri dishes of neurons alive? What's the payoff?
Because biological neurons are incredibly power efficient. A human brain can perform tasks that would require a supercomputer's worth of energy, but it does it on about 20 watts, roughly the power of a dim light bulb. If we can harness even a fraction of that efficiency for specialized tasks, the implications for edge computing or complex pattern recognition are massive. We are hitting a wall with silicon where we just can't keep throwing more electricity at the problem.
So it's about the energy wall. We're reaching a point where scaling silicon AI requires so much electricity that it's becoming a geopolitical and environmental issue. Biological computing offers a potential way around that by using a substrate that has spent millions of years evolving to be the most efficient processor in the known universe. It's a shortcut past the limitations of physics.
Right, and there is also the factor of generalized learning. Silicon AI is very good at specific tasks, but it struggles with what we call out-of-distribution data, things it hasn't been trained on. Biological systems are naturally better at adapting to new, messy environments because they are designed for survival in a messy world. A silicon chip needs a clean room, a biological chip needs a lunch.
It's fascinating, but this is where my mind starts going to the darker places Daniel alluded to. We've talked about the dead internet theory back in episode 593, where the internet becomes a void of algorithms talking to other algorithms. But this feels different. This isn't just a void of code. This is a void of biological matter that is being forced to perform tasks. It feels more like a prison than a processor.
It is a profound shift. When we talk about AI, we often debate whether it's actually conscious or just a very good mimic. But with these neuron chips, we know the substrate is the same stuff that produces consciousness in us. Even if 800,000 cells isn't enough for a sentient mind, it's a piece of the puzzle. It's living tissue. It's human tissue.
And that's the dystopian pivot. We are essentially domesticating human cells to act as circuit components. Think about the ethical implications. At what point does a cluster of neurons become a subject of moral concern? If we scale this up to 5 million cells, or a billion cells, are we creating a trapped, rudimentary mind whose entire existence is just minimizing electrical noise in a virtual environment? It's like a digital version of the myth of Sisyphus, but with neurons.
That's the part that really bothers me. In silicon AI, if the model gets a wrong answer, no one cares. But here, the punishment for a wrong answer is literally chaotic electrical stimulation. We are essentially using a very basic form of pain or discomfort to train a biological entity to do our data processing. We are using the fundamental drive to avoid distress as a programming language.
It reminds me of our discussion on digital twins in episode 7 on 2. We talked about how people are creating these high-fidelity digital versions of themselves. But imagine a future where, instead of a digital twin made of code, you have a biological twin made of your own stem cells. A literal Wetware processor grown from your DNA that manages your schedule or filters your emails. It's a piece of you, but it's a slave to your convenience.
That is a terrifying thought. You'd have a piece of yourself living in a box on your desk, being fed nutrients and oxygen just to serve as a high-end calculator. It blurs the line between a tool and a slave in a way that silicon never could. If you delete a file, it's gone. If you let your Wetware processor die, did you just commit a tiny, localized murder?
And the maintenance aspect is so eerie. You mentioned the carbon dioxide and oxygen regulation. Imagine being a system administrator in 2035, and your job isn't checking server logs, but checking the pH levels of the nutrient broth, and making sure the cells aren't getting a fungal infection. It's more like being a lab technician or a farmer than a computer scientist. The data center of the future might look more like a greenhouse or a hospital ward.
It really is. And the New Scientist article mentioned that these cells learned Doom in a week. That's faster than many humans take to get good at a complex game. It shows that there's an inherent latency advantage in certain types of biological processing, but the stability is the trade-off. These networks are volatile. They can have bad days, they can get exhausted. They can literally stop responding if the environment isn't perfect. Imagine your computer having a mood swing because the oxygen level dropped by 1%.
I wonder about the long-term implications for the tech industry's worldview. For the last 20 years, the mantra has been that everything is data. If you have enough data and enough compute, you can solve anything. But biological computing suggests that the substrate matters. It suggests that there's something about the way life processes information that can't be fully captured in pure silicon. It's a return to the physical reality of existence.
It's a return to the physical. For a long time, we thought of software as something that exists in the ether, something mathematical and pure. But Wetware brings us back to the reality that intelligence requires a body, even if that body is just a thin layer of cells on a piece of glass. It requires a physical environment. It requires energy and waste management. It's messy, it's wet, and it's fragile.
It also makes me think about the security risks. We're used to thinking about hacking as code injection or phishing. But how do you hack a biological computer? Do you introduce a virus? Not a computer virus, but a literal biological virus that rewires the neurons. Or do you disrupt the oxygen supply to cause a specific type of brain damage that changes the output?
You're touching on a whole new field of biocybersecurity. If these systems become integrated into our critical infrastructure because of their efficiency, they become a unique target. You could potentially poison a computer. You could use chemical agents to alter the way a processor thinks. That's a sentence I never thought I'd say, but in 2026, it's a legitimate research concern.
It's wild. Let's talk about the competition between silicon and biology. Do you see a world where they coexist? Or is one going to eventually swallow the other? Are we looking at a hybrid future?
I think they will be specialized. Silicon is always going to be better for things that require absolute precision and high-speed math. You don't want a biological computer calculating the trajectory of a rocket because a neuron might decide to fire a millisecond, late because it's slightly low on glucose. You want deterministic, predictable silicon for that. You want the machine that doesn't get tired or distracted.
Right? You want the donkey for the steady work and the artist for the creative work.
Biological computing will likely be used for things like sensory processing, real-time adaptation, and maybe even creative synthesis. Things where the noise and the unpredictability are actually a feature, not a bug. It's about intuition versus logic. Silicon is logic, wetware is intuition.
That makes sense. It's like having a digital brain for the logic and a biological brain for the intuition. But the cost of that intuition is the ethical baggage and the life support requirements. We are essentially building a brain in a box and asking it to solve our problems.
And let's not forget the geopolitical angle. If this technology becomes viable, the countries that lead in biotechnology and stem cell research will have a massive advantage in the next generation of computing. We're already seeing a lot of movement in this space in places like Australia with cortical labs, but also in the United States and Europe. It's a new arms race, but the ammunition is cellular.
It's interesting you mention that, because as we've discussed before, our perspective is that American and Western leadership in these frontier technologies is crucial. If we are moving toward a world where biological computing is a reality, we want that development to happen within a framework of Western ethics and transparency, as messy as that can be sometimes. We don't want this happening in a basement with no oversight.
Because if this is developed in a vacuum without oversight, you could end up with some truly horrific scenarios. Imagine massive industrial-scale vats of human neurons being used for surveillance or data mining, with zero regard for the fact that this tissue is, at its core, human. We need a Geneva Convention for neurons before this gets out of hand.
It's a heavy thought. Let's move towards some practical takeaways for the people listening. If you're someone who follows tech or works in the industry, what should you actually be looking for over the next few years? What are the milestones?
The first thing is to keep an eye on the term organoid intelligence, or OI. This is the broader field that biological computing falls into. We're going to start seeing more papers and more startups moving beyond just flat layers of neurons and into three-dimensional organoids. These are tiny, lab-grown structures that mimic the actual architecture of the brain even more closely. They aren't just a layer, they're a structure.
And those three-dimensional structures would presumably be even more powerful than the flat chips.
Much more. They have more connections, more complexity, and they can process information in ways that a flat grid can't. But they are also much harder to keep alive and much harder to interface with. The breakthrough will be when we find a way to reliably read and write to those three-dimensional structures without killing them. That's the holy grail of wetware.
Another takeaway for me is the shift in maintenance. If you're in IT or systems engineering, the skill set is going to start overlapping with biology. We might see a world where the most valuable people in a data center are the ones who understand fluid dynamics and cellular metabolism as much as they understand networking protocols. You'll need a degree in biology to fix a server.
It's a blurring of disciplines, and for the average person, it's worth reflecting on what this means for our definition of life. If we start interacting with devices that are powered by living cells, does that change how we treat our technology? Do you feel more guilty about throwing away an old phone if you know there's a small cluster of living tissue inside it that helped it learn your habits? Does your phone become a pet?
We already have people who get attached to their Roomba or their AI chatbots. If there's a literal biological component, that attachment is going to be even stronger. We might see a movement for robot rights that is actually a movement for the rights of the biological components inside the robots. It's a whole new frontier of civil rights.
It's a strange new world, and it's happening faster than people realize. The fact that these cells learn Doom in a week in early 2026 is a massive benchmark. It's not a toy anymore. It's a proof of concept for a functional, adaptive biological processor. It's no longer a question of if it works, but how far we can take it.
I also think we need to be wary of the marketing. Companies will frame this as green computing because of the energy efficiency. And while that's true, we have to look at the total cost, including the ethical cost and the specialized infrastructure needed to sustain it. Don't let the green branding distract from the dystopian reality of lab-grown brain tissue in a box. It's efficient, but at what price?
It's the ultimate black box. We don't really know what's happening inside that network of neurons, we just see the inputs and the outputs. It's even less transparent than a neural network made of code because we can't just pause the biological process and inspect every single state. It's alive, and life is messy and unpredictable. It's the opposite of the deterministic world we've built.
So, as we wrap this up, what's your final verdict, Herman? Is biological computing a dream or a nightmare?
I think it's a bit of both, but mostly it's a reminder of our own complexity. We are trying to build machines that are as smart as us, and we've realized that the easiest way to do that might just be to use the parts we're made of. It's a shortcut that comes with a lot of baggage. It's fascinating from a scientific perspective, but as a human, it makes me want to hold on to my own brain a little tighter. It makes me appreciate the 86 billion neurons I have that aren't hooked up to a microelectrode array.
I feel the same way. It's a humbling reminder that for all our progress in silicon, we're still trying to catch up to the efficiency of a single petri dish of neurons. But I'm not sure I'm ready for a computer that I have to feed and worry about killing if I leave it in a cold room. I like my hardware cold and dead, thank you very much.
Yeah, I think I'll stick to my noisy fans and power cables for a while longer. At least I don't have to apologize to my laptop when I shut it down for the night. I don't have to worry about its pH balance.
Well, this has been a deep dive into some truly weird territory. Thanks to Daniel for sending this prompt in. It's definitely going to have me thinking about my devices differently for the rest of the week. Every time I hear a fan kick on, I'll be glad it's just air and not a lung.
Definitely. And if you're out there listening and you've got your own weird prompts or topics you want us to explore, please get in touch. We love the feedback we've been getting from the community lately. It's what keeps the show going, even if it gives us nightmares.
Speaking of the community, if you've been enjoying my weird prompts, please take a second to leave us a review on your podcast app or on Spotify. It genuinely helps other people find the show, and we love reading what you guys think. We've been doing this for over 1,000 episodes now, and it's the listeners who make it worth it.
It really does make a difference. And if you want to make sure you never miss an episode, you can follow us on Telegram. Just search for My Weird Prompts, and you'll get a notification every time we drop a new one. We're also active in the comments there if you want to debate the ethics of wetware.
You can also find our entire archive, including those episodes we mentioned today, like episode 593 on the Dead Internet and episode 702 on Digital Twins, over at myweirdprompts.com. We've got an RSS feed there for the subscribers and a contact form if you want to reach out to us directly.
We're always looking for the next deep dive, so don't be shy. Whether it's biological computing, geopolitics, or the latest in hardware, we want to hear what's on your mind. We want the prompts that make us uncomfortable.
All right, that's it for today's episode of My Weird Prompts. I'm Korn.
And I'm Herman Poppleberry. We'll see you next time.
Take care, everyone. Stay curious, and maybe keep an eye on your hardware. You never know what it might be thinking.
Or what it's breathing.
Goodbye.
Bye.
So, Herman, do you think we should tell Daniel that the next time he sends a prompt about brain cells, he should maybe include a disclaimer about the nightmares? I'm serious. I'm going to be looking at my phone like it's a sentient hamster all night.
I think he knows exactly what he's doing. He probably sat there in the kitchen and waited for us to read that New Scientist article just so he could see the look on our faces. He's probably listening through the door right now.
You're probably right. He's probably growing a Doom-playing organoid in the basement as we speak, just to see if it can beat his high score.
Don't even joke about that. I'm not sharing my internet bandwidth with a petri dish, and I'm certainly not buying it a nutrient broth subscription.
Fair enough. Let's go see what's for dinner. Hopefully nothing that requires an incubator or a precise CO2 balance.
I'll check the fridge. If I see anything that looks like it's trying to learn a video game, I'm moving out. Catch you later.
See ya. Thanks for listening to My Weird Prompts. We'll be back soon with more deep dives and brotherly banter. Until then, keep those prompts coming.
And keep those brains active. The biological ones, I mean. The ones that aren't on a chip.
Cheers.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We shake.